Welcome back, everybody. This is the third and last session for today. We're here at the first edition of the Developers Conference, version 1.0, beta release 27.0 something, right over there? Okay, I hope you guys enjoyed the lunch and the break and the conversations and the networking. We're going to have a bit more networking after this session and more wine. So it wasn't just a teaser. You guys actually were able to taste it. Our next speaker, Richard, actually came here with an unfortunate mission to speak right after lunch break. So I think he's going to make us move, a bit of, do a bit of moves of martial arts, given the title of his book, The Tao of Microservices, right? Any special move? All in here, okay. I think before we actually start, I want to go back to what I said at the beginning of the conference about the passion that is bringing us here and how passion is driving us into doing things differently, not just coding and writing code and building apps or services or products. And for instance, you've seen Danny, who out of passion for what we are doing as a development community, he's been investing into other startups, and he's trying to do more than just, build a product and do something as a business. Then we had Peter, who you've seen that is contributing quite a lot to the community by answering quite a lot on Stack Overflow, and now working on open source. And then we have Richard, who's contributing, to the overall knowledge by publishing books and by building open source projects for a lot of developers to use. So all this, in my books, is passion, right? And I'm sure every single one of you has that kind of passion, but you maybe haven't found a way to externalize that, just like our speakers did. So hopefully you will find the answer, and next year we'll probably see some of you on stage. The topic that Richard is going to cover is one quite dear to my heart, but I really hope that you guys are going to be as active as for the previous ones and stop me from making too many questions. Okay, and this time I know we have a prize for the most complicated question for Richard. Okay, so without further ado, let's give a big hand for Richard, and the stage is yours.
Can you guys hear me okay? Yeah? So I want to talk about microservices. I noticed you're really good at questions, much better than most audiences. So I brought a copy of my book. This is...
I sound much better. This is fantastic. I'm really delighted to be here in Cluj, now that you can hear me. It's a lovely city. And sunny, unlike Ireland, which is good. So I brought the book that I wrote about microservices. This is for the most difficult question afterwards. That will be difficult to decide because I noticed you all asked very good, difficult questions. I'm talking about microservices because they were something that in my previous company, which was an IT consultancy, that we ended up using. The reason we ended up using the microservice architecture is because we originally chose to build systems in Node.js, which means building systems in JavaScript, which, if you've ever used to build systems, you'll know is a really bad language, really bad at providing you with structure, unlike Java or C# or something like that. So it forces you into creating your own external structures, which is how we ended up with microservices. So it wasn't a deliberate choice, but it was a choice that we ended up using for a lot of enterprise projects. So a lot of the time, I talk about what I've learned in terms of building these systems and how we go about designing them. And sometimes the most powerful things that you learn, it takes a little while to understand what you've learned. But I think the most powerful things are the mental models that you build, which make you more intelligent. But I'm going to start with a different question, which is, how did the Romans do long division? So if you think about Roman numbers, and you were asked to do this problem, which is 3,612 divided by 72. How would you do it? What is the algorithm? If you were 2,000 years ago in Cluj, and you are a bookkeeping slave and you have to calculate this mathematical problem for your Roman master, how do you do this? What is the algorithm? It's a difficult problem because the representation is difficult. Let's make it a little bit easier. So how do you do addition? It's simple, but it's not as simple as you think. This is the algorithm. So you have to normalize the representation first, then you concatenate all the numbers together, then you have to sort them, and then you get the answer. So it's reasonable, it's easy, but it's still not a very good mental model for numbers. How do you do subtraction? It's kind of the same, except now you have a for loop as well. You have to normalize again, eliminate things in both operands, expand them out so that you can find the same representations. And you do a for loop. You keep doing that until you can't get any simpler. And then you reduce your representation down to the form that humans expect. That's addition and subtraction. What about multiplication? So how do you multiply two Roman numbers together? So the Romans invented bit shifting to do this problem. So if you read about this problem on Wikipedia, the way that they actually did it in practice was to get two rows of counters or stones and then eliminate this. They had a little algorithm where they eliminated stones, but it is essentially bit shifting. So you take the number, take one of the numbers, turn it into its binary representation, shift the bits, multiply it out by 2, and add it all up at the end. That's how they did multiplication. So already you can see that the algorithms that they were using previously for addition and subtraction are a different style of algorithm, a different way of thinking to multiplication. So you are seeing that Roman numerals as a representation system, as a way to think about numbers, are weak because you have heterogeneous algorithms to do things. So let's get back to that question, right? How did they do division? This is where you have the correct answer. They didn't do division. They used multiplication and they estimated, and then did the last piece by hand. So if you look at those two number systems, you can see, if we think about it in our modern day terms, Roman numerals have technical debt. And this is not just it's not just a funny statement, it's a true statement, because Roman numerals came from sticks of wood that were used to count sheep and goats. And you make a mark for 1, and you make an X. You can see how with a knife you can make an X easily, or a V shape. But you're left with this technical debt afterwards because your implementation is for a different time. And now if we look at a different system, if you ask the question, how did the Indians do division, which is how we do division today with our base 10 number system, you can see it's much easier to do the operation, even in your head. Half of 72 is 36. You can already see that 50 is the right answer. You can see that there's 12 left over. In 2 or 3 seconds, you know this is true because you can see it. Because the mental model, the representation of the numbers, is a better model. All the operations that you perform are operations that have all the algorithms have the same structure. And this is the place that we want to get to with building software systems, where to do all the things, perform all the operations, it's always the same style of thinking. It makes you more intelligent. It lets you build bigger and more complicated systems. The question we have to ask is, what mental model are we using to build our software systems today? Is it object-oriented programming? Is it functional programming? What is the mental model of the infrastructure, the physical system that we're building. If you haven't asked this question, you're relying on the mental models that other people have built, and you're relying on the technical debt that is built up in your system, made by choices of the software architect who now works in a different company. There's this anti-pattern called the lava flow, where a system starts off with a unified design, but then a new architect comes on board and they take the system this way, and then they leave. And then another architect comes and starts back here and slowly changes the system that way, but you're still left with 50% of the old code base because it's too much work to change. And you get this horrible, messy flow of lava down the side of the mountain. And that's the system that's live after 10 years that you have to work with. What we need is a way of combining abstract concepts. And that's called, in mathematical terms, an algebra. It's a set of operations on well-defined types. And if we can think about our software architectures, if we can think about microservices in this way, we get a very easy way to comprehend the systems that we're building. So going back to our Indian number system, our decimal number system, you can see that all these operations can all be performed using the same type of model. But the interesting thing about this, the thing that makes it an algebra, is the fact that we're always taking numbers into an operation, and numbers are always coming out. Now, I know there's some complexity around, are they sets of numbers, that sort of stuff, but we are maintaining a homogeneous set of types. The important thing, conceptually, is we're looking for a structure where you put things in and the same types of things come out. And if you have a mental model with that type of structure, you have effectively an algebra, and you have a very clean way of thinking about the design of a system. Here's a set of operations on a database, structured into this algebra idea. So my database is just an ordered list of records. And when I do my create, read, and update instructions, I'm taking one database and turning it into another database. I'm not turning Postgres into MySQL. When I say database, I mean the static representation of the data into another static representation. But it's one database into another. It's the same thing. It's an ordered list in and an ordered list out. If we can define operations on our business logic in the same way, then we have a structure that lets us easily communicate what the system is supposed to do. If you look at what actually happens when you do an update to a data record, it doesn't look like that at all, because you're also doing logging and permission checking and data validation and all sorts of other things that are additional, they're external to the pure algebra, which is just adding an entry or changing an entry in an ordered list. So if you think about it, this is actually what's happening. We're going from my ordered list plus a whole bunch of context around the user and their permission, special cases because the third architect of the system added in a small optimization. I'm not going from the same type of thing to the same type of thing. I don't have a simple way to describe the system because all this complexity has come in. And I think this is actually because in our search for expressive power, our programming models have developed too many features. So the standard solution to this problem, and I'm sure as developers you have built things like this or used things like this, is to say, well, let's just use components. We encapsulate our complexity, and then we have a component model. But have we, in fact, up to now, up to 2018, come up with good component models that don't also descend into complexity? And I think the answer is no. I think that things that have attempted to be component models have failed. And this is the proof. So put up your hand if you're an object-oriented programmer, if you use an object-oriented language, which is the majority of people. And before I started using a toy language like JavaScript, I did Java for 10 years. And it's an object-oriented language, and you have inheritance, and you have encapsulation, and you have polymorphism, and Java, the latest version of Java has all sorts of annotations, all sorts of fun stuff. Why do we need this book? Isn't the promise of object-oriented programming that you are given enough tools and structure to build software anyway? And now I need to know design patterns on top of the tools that I'm given? This is proof that the tools don't work. This is proof that the object-oriented model isn't strong enough. It doesn't let you represent complexity. Objects are supposed to be reusable, are they? Not really. So the object-oriented model was trying to solve a problem, but I think it failed. I think this book is the proof, and that book was written 15 years ago or something, or even earlier. So our search for a component model that works isn't done. We still have to keep searching. We still have to find something that makes our lives easier and gives us better mental models. Let's think about what we want in a component. And I'm just going to put up 4 or 5 attributes, and there are more. You could have extensibility, things like that. Reusability is supposed to be the big thing. Surely it's well-defined. Surely you have a strict interface so you can tell if the things you're being sent are invalid. Loosely coupled and coherent. Independently deployable. We've kind of solved that problem now with things like Kubernetes and Mesos and serverless functions. Things do advance. It's not all bad news. They should be composable, right? They should be like Lego. This is the whole point. You have to compose things together. Isn't this what you're supposed to do in object-oriented programming? And the first version of that you were taught is inheritance models, and then they became the bad way to do things, and now you're supposed to compose objects together by keeping references inside objects, all that sort of stuff. So there's a set of characteristics that you might want, but we have to think about what are the important ones? What are the ones that give us this easy way to think about the system? What is the thing that makes components powerful, that actually does the job? And I think we have to focus on the very simple problem that we're trying to solve. Like building a spaceship out of Lego. You want to build big things out of little things. And if you can't easily put the little things together, it's not a good component model. Just to go back to the mathematical models, here's a polynomial equation, but it's composed of all those simpler operations. It's easy for us to create complex abstract structures because we've set up an algebra, because we have simple operations and simple ways of combining them. Compare that to object-oriented languages, which have tons and tons of features. Every new version of Java gets new features. You don't get new versions of the integers every 10 years with extra features to make them more powerful. That's not how it works. The thing that you need is composability. The thing that gives you big things out of little things is the ability to put pieces together. It's much more important than reusability or extensibility or coherence or any of that stuff. It's composition that counts. And you get that if you think like a mathematician, if you try to define something that's like an algebra. You take a type of thing and you get the same type of thing out. But how do we actually make this happen? You need things that are easy to combine. So we have to think about what does it mean? Why is it that Lego bricks are easy to combine? What is it that makes them easy? Here's an example of some component models and how complex their interfaces are. So if you think about command line tools where you just have streams of text. You just pipe the output of one command into the input of another. It's essentially a single dimension. Compare that to HTTP, where you've got verbs and you've got the headers, and they have their own little formats, or compared to functions or objects, plugins, right? There's 1,000 plugin models, but they always have a life cycle. If you use React or Vue.js, or any of the server-side models as well, they always have this type of stuff. You can see that these interfaces have very high dimensionality. There are lots of different types of things. A HTTP verb is not the same type of thing as the contents of a header. It goes in a different place in the format. The lifecycle events of a plugin are different from the standard methods that you might provide to provide functionality, the list of the hooks into the system that you have to call. They're all different types of things. That's why these component models don't really work. And if you think about another aspect, which isn't as apparent, but is really fundamental, is this idea of identity. Identity in the sense that in order to use something, I need to know its name or its location. So if I have to make a HTTP call, I've got to know the network endpoint. Ultimately, I've got to know the IP address and the URL path. To call a function or an object, I need a reference or a pointer. The plugins need to know what the integration hooks are. If I'm using a message bus, I need to know what the topics are. Interestingly enough, on the command line, there is no identity. You don't know the name of the command that you're piping stuff to. You just send text out on standard out. Somebody will receive it. You don't know who it is. That's very powerful. If you get rid of this concept of identity, it gives you composability. It's part of the secret sauce. It's part of creating a mental model that makes it easy to put things together. If you look at an object and you want to swap it out for another object, and inheritance is the way that you're supposed to do that, a lot of the time it fails because there's a lot of complex internal state. There's a lot of other dependencies. You've used other features of the programming language, which means that the pieces don't quite fit together. There are temporality issues in terms of the ordering in which you have to call methods, all that sort of stuff. So we just try to push all this down into the simplest form that we can manage. We have to reduce the complexity of the interfaces, and we have to reduce the knowledge that components have of each other. If we can do those two things, you start building a component model that can actually work. This dimensionality thing is a really enticing, seductive mistake. And every time, part of the reason that I left Java is, and I got to 1.6, I think, is because every time there was a new version of Java and there were new features, it made me very sad. And the same thing happens with JavaScript now. This safe place that I went to is now suffering from the same thing. Every new release of JavaScript has new features and extra things that you can add. And I think it's a big mistake. I think it's not. It seems like if you add features to a language, you get more power, but you don't. You just get a bigger mess. But microservices are, I think, an opportunity to do something different, and a thing that can insulate you from the complexities of a language. Because I think they're an opportunity to build a component model that works. You have to do it in the right way. So a lot of the criticism that I see of the microservice architecture is based on building microservices in a programming language style, where you still have these concepts of identity. You have to know which microservice you want to call, or where you have a well-defined interface, like you use Swagger or something like that to define an interface. So now you've just made your life much more difficult because you have a configuration deployment issue and you've got the network. You might as well go back to a monolith because then it's just function calls. So of course, those criticisms of the microservice architecture are valid. Some of the ways that people get around that is doing things like service discovery. So, Kubernetes provides you with an inbuilt DNS server, and Docker will give you little names for your containers, that sort of thing. It's half a solution because those names are still identity. You still need to know which microservice you're calling. If we think about the standard way the microservices are built, little web servers, REST APIs, they're not composable. You can't put them together because you have this interface complexity. If you have a strict message schemas, again, you prevent easy composability. If you have even message buses, you use Kafka or something like that, which is, again, a good solution in many ways, but the topic name is an identity. So you don't get this easy composability. What we have discovered in the work that I did in my last company is that there are two essential attributes, features, that give you this composable model. One is transport independence, and the other is pattern matching. So transport independence is the idea that you don't have identity and you don't know how messages go from one place to another. You don't care if it's HTTP or a message bus. It's irrelevant, or even a function call. And pattern matching means that you don't route messages explicitly. It means that you can decide dynamically as the system runs where a message goes. And so in that way, each individual microservice lives in its own universe. It doesn't know what other microservices are out there. Its entire world is concerned with receiving messages and sending them out again. If we think about this, you have to represent it in a very strong way. So this diagram could be two programming objects of any kind. They could be functions or objects or classes or whatever. But if we say these are microservices in a transport-independent world, you can't draw this diagram. The only diagram you can draw is this one. All you can do is send and receive messages. A and B know nothing about each other and never will. If we think about the pattern matching side of things, the way I'm going to represent this to avoid writing code is with playing cards. So the B microservice accepts any messages that have a certain pattern. Now, are you using a binary encoding for your messages, or JSON, or XML? It doesn't matter. And it doesn't matter what the pattern matching algorithm is. Is it a regular expression? Is it equality on a few properties? Is it the center of the message? It doesn't matter. But the point we're making here is that the B microservice will accept any messages that match a certain pattern, and the A microservice has sent out a message that does match that pattern. So somehow, the King of Hearts gets to B. Somehow that message goes from A to B. Transport independence means you don't know how. But that's important. It's important not to know, because that gives you the freedom to swap and change the microservices. And this is where we start seeing some usefulness in terms of composability, because it lets you do interesting things. For example, you can scale your system without designing scalability. If you have a message routing system that ensures that transport independence and pattern matching are basic infrastructure, if you write one microservice that handles a particular pattern, and then your website becomes successful or whatever, and you need to handle a higher volume of those messages, you just add more instances. You don't need to configure a load balancer. You don't need to think about setting this up. It's just there. You just add more instances of that microservice. And scaling down is the same. So you get scaling for free. It's a side benefit of the composability. If you want to do different things with the same message, you can add different microservices that react to the same patterns. So in this case, B and C do different things. The same business event, a checkout button on a shopping cart was pressed. You've got to send an invoice email, and you've got to send a message to the warehouse to send the goods, and all the other different things. But A doesn't know that I have to call the invoice microservice and call the warehouse microservice and call the auditing microservice and update the database. It just sends out a message, and it's done. C doesn't have to be a different microservice. It can be a different version of the same microservice. So you can deploy a new version of your functionality and only send 5 or 10% of the traffic through that functionality. Again, yes, the infrastructure does have to have a little bit of complexity to manage that. But with the pattern matching, it's relatively easy to add in. It's not a huge amount of work. One of the criticisms that you hear of microservices is build a monolith first, because there's lots of work involved in setting up the infrastructure. But if you take this approach to messages, there isn't. You can lean on Kubernetes and things like that, and you don't have to worry so much about setting it all up. Another interesting thing that you can do, and this is an important slide. So in programming, we are often taught to generalize. You write a couple of lines of code, you write the same couple of lines of code a bit later in your file, turn it into a function. Don't write the same code 3 times, right? Dry, don't repeat yourself. Our thinking is so strongly focused. We have this major mental model on generalization that we've forgotten about the power of specialization. And in reality, when you're trying to build a software system that solves a business need, you need to specialize, not generalize. For example, if you're building a user login system, the first thing that you do is build a small microservice that just handles user logins. It's only later that you start worrying about user logins in Europe now need to worry about GDPR issues versus user logins in the US. Or what happens if you're an employee versus a contractor? Do you see a different page after login? This type of stuff. But when you're building the MVP in the first version of the system, you build a simple microservice that just handles logins in general. Only later do you add new microservices that handle special cases, which means that you don't have to change the general case, which means that code never becomes complex, which means you don't have to add additional items to your data structures, which means you don't build technical debt. Add a new feature by adding a new microservice. And then we get to the most powerful bit, which is composition. Because in my original structure, A sent a message and it ended up at B. But if I wanted to do things to that message, to validate that message, to add additional business logic, to do other things, I can intercept the message and modify it. So C does other things. Maybe it's validating, maybe it's auditing, who knows? B and C now form a component, a thing that handles the King of Hearts. But as far as you're concerned, when you're thinking about the system from the perspective of A, you're just sending out the King of Hearts. You don't have to worry about all that complexity. So you've built a more complex thing from smaller parts. Just because the parts are independent and you're using pattern matching to put them together. So the pattern matching is like the little studs on the Lego bricks. It's the thing that lets you put the pieces together, and the whole thing still works. To make this work, you can't have strict schemas. Okay, that's a whole bunch of theory. Let's look at an actual system. How can you turn these ideas into? Somebody gives you a software specification, you have to build an MVP. How do you go back to the real world? You have to decide which microservices to build, because ultimately that's where your code lives. So the methodology that we follow is we take a look at the business requirements, then we turn them into messages, and only then do we turn them into services. So messages come first. You don't take a look at the functionality and say, we need a service for this, and we need a service for that. You don't do that. You think about how the business requirements are represented as messages. And only then do you say, let's divide the messages into different services. So I'm going to take you through an example system. I was talking about user registration. So here's an example of going through that process. You got to capture the user's details. You got to send a confirmation email. So let's informally just think about messages that we might build, right? So there's a register user email register user message and a confirm email message, and they're JSON documents, and register user as name and email. Just make it up. It doesn't really matter. You don't, because you're not being strict about your schemas, because you're going to expect a lot of requirements change, it doesn't matter. And from those messages, it then becomes clear that there's a service that has to send the message. So registration sends register user to the user service sends confirm email to the mailer service. And you can represent that in a diagram. So the hexagons are microservices, and that's the message flow. But conceptually, we can say that the registration service is a component. And mailer is a component of that registration service. And it may be a component of other services as well, because they need registration as well. But from the perspective of the user service, mailer doesn't exist. So you're putting these things together, hopefully, like Lego. Things are never quite as wonderfully easy as they first appear. There is an extra dimension. There is an extra dimension that you have to handle in this model, which is a temporal dimension. These messages can be synchronous or asynchronous, so you have to represent that somehow. And also, there can be one message or many sent between services. So for example, in this case, this is a request-response model like HTTP. It's synchronous, and the message, when it gets to microservice B, is consumed. Only one microservice sees it. So you can see there's 4 different alternatives here. You can have a publish-subscribe model where the message is sent out to lots of different places, lots of different people see it, there is no response. But you can also send out a message to lots of different places and get lots of different responses. So for example, if you're doing insurance quotes and you're using different algorithms, things like that. And finally, you can send out a message to lots of different services, and only one of them will act on it. This is a classic work queue. So if you have a whole bunch of microservices that are resizing images, you don't want to resize the same image multiple times. That's a waste of CPU. You put it on a work queue, and there's a whole bunch of services that take the next one. And I can freely say put it on a work queue because transport independence means that I don't have to have HTTP or that as my standard communication protocol. I can use whatever I like because I've abstracted that all away. And if you look at these diagrams, they follow a very simple convention. So are they synchronous or asynchronous? Are they consumed or observed? This lets you represent the system. And we are relying, like I said, on a message abstraction layer. Is it HTTP? Is it Kafka? We don't care. There is a utility library in our microservices that handles all that for us and looks after the pattern matching and all the complex stuff. So here's an example of building an actual system. We'll go through the various pieces here so you can see how the components fit together. So if you use Node.js, you'll know that there's npmjs.com is where you can find, I think it's 700,000 Node modules now. Let's build a little search engine. So you can type in, I want a HTTP client or something like that and find a result. Here are business requirements, 3 of them. Search for the modules, index them into Elasticsearch or wherever, and then show the details of a module. So by the details, I mean its GitHub page, its NPM info page, maybe the Traverse results, maybe the latest tweets, who knows. And if you go to some of the links at the end of this presentation, there is a demo system that you can build to show this. So here's a search and search results, and then the info page for this particular module is just from NPM and GitHub. So let's go through this process. A requirement is search for modules. We'll get a little bit more specific about messages now. So we'll actually define the patterns. We won't just give them abstract names. So they're JSON documents. They have random properties. If a message has a property role equal to the text string search and a property command equal to the text string search, I want to send it to the search microservice. And it's a synchronous message because you expect to get a list of results back. So if you make a diagram of that, the web microservice provides my front end. Search does the searching. It probably talks to Elasticsearch. I don't know. But this diagram doesn't mean that web knows about search. It means that my routing logic is doing a pattern match on role search, command search, which is a convention I've just randomly invented. Right? It's not the name of a method. It's not identity. I could have different versions of the search microservice. I could implement it in a totally different way. I could be trying out a different, I could be trying out Solar instead on half my traffic. And that would use a different service. Index the services. So I want to go to the npm.js website, and every time somebody publishes a new module, I get a big JSON document with a load of information. I want to put that into Elasticsearch. So command insert in this case. And I'm using role because there may be multiple microservices implementing this particular piece of functionality, not just a single one. So let's have an npm microservice that sucks down data from npm. And then it is asynchronously pushing data into the search engine. So it's just sending out messages. It doesn't know that there's a search engine that will index them. Its job is just scrape data from websites, emit an event that says, hey, I've got new data. And then finally, we have to show the information. So the web microservice needs to talk to an info microservice. And we're getting kind of used to this pattern now. There's role info command get, and it gets the information about the microservice. So you can diagram it up like this. Web sends a synchronous request to info, because I have to display information for the user right now. But the problem is, that information comes from multiple places. NPM, GitHub, Travis, Twitter, who knows? So I want to collect that information from a number of different sources. So I send out a publish subscribe message. I emit a message saying, give me information. Everybody who gets that, loads of different microservices, will react and emit another message saying, here's some information, don't know who asked for it, but here it is. So in our case, we've only implemented NPM and GitHub. And we end up with this model where info sends out need part. NPM and GitHub see the need part message, and they respond with collect part. And again, I've just invented those names. That you can use whatever conventions you like. We're just matching the patterns of the messages. Again, from the perspective of web, info is a complex microservice that knows how to talk to GitHub and knows how to talk to NPM and knows how to do all sorts of wonderful stuff. But it's not. It's a system of components that we've put together because the only interface we have to worry about is a small set of patterns. We don't have to worry about, is this a static method? Do we have to provide properties? Do we have to call them in the right order? Our entire description of the interface that joins these components together is just a simple pattern. And you could do complex pattern matching if you want. I don't recommend it. It's very easy to build large systems just on this basis. Here's a real system. So this is from about 6 months ago, a system that I built for a client. It's a content management system. It's fairly easy to kind of just sit there for an hour in a meeting and design up a system. And this is the heart of this idea, right? It's not just that microservices are scalable or easy to deploy or that serverless architectures, and serverless is just sort of extreme microservices. It's not just that they're independently deployable. It's not just that you can, build a feature in the morning and get it live in the afternoon. I think the heart of the idea, the thing that really makes your life easier as a developer is it makes you more intelligent. It makes you more able to build complex systems faster. That's a different problem from building fast, complex systems, by the way, which Peter was talking about earlier this morning. It's a different engineering challenge. I'm talking about the challenge in the first 6 months of a new project where the client doesn't know what they want and they give you a specification which is badly written and underspecified, and they keep changing requirements. You keep having to change your data models and all that sort of stuff. Using a good component model makes that easy because last week's microservice with a data schema that is now incorrect, you just throw it away. You just rewrite the microservice because it was only a few days coding anyway. So this is where we kind of go back to thinking about an algebraic structure that we've created. And we're not real mathematicians. This is just a very simple mental model that we're using. If we think about it algebraically, messages are operations on data. When a microservice gets a message, it changes state in some way. So I've got to write it up in fancy mathematical terms, right? It's a mapping from the data to another set of data. But you can also think of microservices as operations on messages, because a microservice takes in a message and generates more messages. So if you think about it conceptually, when you think about what your microservice does, you express that as its operations on messages. You express it as the messages that come in and go out. You don't think about it in terms of the internal logic of the microservice. And the reason that works is because if you started with the business requirements, you've expressed them as messages and then only implemented them accidentally as services. The implementation doesn't matter. And this is what gives you composition, because it gives you an algebraic model that lets you put things together. Let's go back to this user registration idea. Now here's a simple representation of a user registration microservice, and it receives a register user message, updates the database in some way or whatever. This was your MVP, but unfortunately on May 25th, your MVP is going to have to handle GDPR. So you change your system. You dynamically add new microservices to the system. You compose components together. One of them handles personal data, which is stored in a different database, which is encrypted at rest and all that type of stuff. But your user profile data, which is storing your preferences and all that sort of thing, which is not personal data, can go in a different place because you don't need to delete it on demand or anything like that. Our first version of the registration service, version 1.0, just wrote directly into a user table in the database. It didn't handle this complexity at all. When this complexity came along, we could decompose it into 3 components. We could write a user profile microservice that accesses a user profile table. We could write a personal data service that accesses, possibly a totally different database. And then we have registration version 2, which we could deploy alongside version 1 and let them run for a few days until we know everything is okay, except that 2 handles all this complexity. And eventually we remove 1. And yes, I've completely ignored the whole data migration issue, but again, that's not a particularly hard problem to solve because you could replicate messages and send them to both places. Again, the pattern matching makes that easy. But the main point of this is that these are all my components that I've put together so that I can have this mental model. I can stop worrying about exactly what happens. And because I have a way of controlling this complexity, I don't allow complexity to bleed into other parts of the system. I don't allow technical debt to build up. I don't have to build a data structure that can handle this complexity, because I have a simpler data structure in user profile and a simpler, different data structure in personal data. Over here in the old system, where you have an object and you have business logic inside your object, you probably do have to add to your database schema to handle these different cases. At least, if you're a really good software developer, you probably do add internal interfaces. This is another criticism that people have of microservices. They say, just use the tools you already have. Just use object-oriented interfaces. Just do it properly from the start. You don't need to have all this fancy microservice deployments in Kubernetes. The problem is our tools are too powerful. It's too easy for a junior developer to destroy the senior developer's work. Not because they're evil, just because they don't know. Because they're under deadline pressure, and it's easy to break the model. It's not so easy to break this model because these messages are going over the network. It's much harder work. You might as well just say, I'll write a new microservice, and I'll put all my rubbish junior developer code into that microservice. But at least it's insulated from everybody else. And it's the right way to do it. Then you can have an argument about, are these the right messages? Not, is this 20 lines of code the right implementation? Arguing about a few messages is much, much easier. So just to push the algebra metaphor as far as possible, it's a really weird inversion, because you think about messages as being a command that you send to a microservice. But if you adopt a different mental model where you say a microservice is an operation on a message that generates new messages. It takes one type of thing to the same type of thing. Now you have an algebraic structure which lets you design your system in a much simpler way. And yeah, that's crazy, because in the real world we don't think about things that way at all. But it does give us a simpler perspective. It does mean that there's a fundamental abstraction that is powerful and safe and won't generate too much complexity. So what do you get for all this work? What do you get for all this twisting your brain around in really weird ways? Well, I said this already, right? If you're building new requirements, generally, it's a new message and a new microservice. And you don't have to change old code, so you don't have to refactor. That means you can move really, really fast. If requirements change, if you've already built part of the system and the client changes their requirements, which they always do, instead of changing your code, instead of refactoring a microservice, you add a special case microservice. Leave the general case alone because you know it works already. Add a new microservice that handles the special case. It's a strange way, perhaps, to do software engineering, but the cumulative effect is that code doesn't touch each other. The data structures don't grow in complexity. And the technical debt is contained in a little bubble inside each microservice. You can analyze your messages. I'm not saying that the message structure and the message flows and the relations between microservices do not become complex. But you're handling that complexity because you're thinking about a simple model. You're saying, do we have too many messages? Is this message flow at 10 steps a complex message flow or not? But it's all the same type of stuff. Those are good arguments to have. When you're arguing about your architecture, but you're stuck inside the code, inside for loops and while loops and higher order functions, it's difficult to see the architecture because the code is in your way. Technical debt is something that then you can not remove, but something you can choose. It's something that I do with every project now, because every project has developers of different skill levels. Different microservices have different unit testing requirements. For this microservice, which is a back-end batch job, 20% coverage is fine. Give it to the junior developer. It doesn't need to be higher quality. This one over here, which is part of the shopping cart checkout process, 100% coverage, one of the senior people has to write that one. You can choose how you adjust your quality because you always have limited resources. You never have enough time to make the whole system good. But you can decide where you accumulate technical debt. Where do you take out the loan? Which bank do you take the loan from? This one is an interesting question. Because you build the system, there's lots and lots of network traffic. It is slow. You have you have given your system higher latency. But if you stick to this transport independence and message patterns and pattern matching model, that makes function calls in the same process just another transport. So you can take two pieces of code that are running as independent processes, put them together in the same process, so you no longer have network traffic, without changing your code at all. It's perfectly natural because you've stuck to this simple model. So you can identify the bottlenecks in your system. You can identify where performance is a problem, put those services together. After 6 months, after you've validated your business model, after you know where the traffic is going to be. I know that doesn't apply in all cases. Sometimes you're replacing an existing system. You can predict where the traffic is going to be. You still build it as separate microservices because it makes it much easier to validate. But you know you've always got this get out of jail where you can put the things together. You can put them into the same physical process to reduce that latency. And finally, well, I have a whole totally different talk about this, but because you have this algebraic structure which defines the relations between messages, you know what they're meant to be. If I press the checkout button and there's a checkout message, there needs to be two other messages, one that sends an invoice and one that goes to the warehouse. And if I measure this and I see that there's 1.5 messages generated for my one checkout message, that means that 50% of the time the invoice microservice is failing. So I can monitor the expected relations between the message flow rates. And I can determine if things are going wrong. That means if I deploy a new version of the invoicing microservice and 10% of my traffic is flowing through it, but suddenly I'm only getting 1.85 or 1.9 messages for every one message in, I know it's broken. I can trigger automatic redeployment of the older version of the microservice. There's all sorts of fun stuff you can do with this. Massive topic. I'm not going to get into it anymore. But by thinking about your system in terms of messages, not in terms of code or data structures or any of that type of stuff, you get additional powerful ways of observing the abstraction that you've built. Okay, so there is a practical open source implementation that we use, Seneca.js, but it is a Node.js system. If you code in a different language, it can be used as inspiration. There's no rocket science in this open source project. All it does is make sure that you have a message abstraction layer that hides whether it's Kafka or HTTP or whatever, and does pattern matching on JSON documents. If you have those two things, in reality, implementing that is a couple of hundred lines of code, and you get all this power. This open source project has a plugin architecture and all sorts of other stuff. But you can look at it as inspiration if you're coding in Java or C# or something else. If I have been somewhat confusing, I talk in much more detail and in a more structured way in the book about all these ideas, about how you put them together. And then finally, this is not an abstract idea. There are people who are kind of architecture astronauts who invent architectures and then just talk about them at conferences all the time. I'm building a new startup at the moment, a social network for people at conferences and event organizers and that sort of stuff. It is 100% using this approach. So we're putting our money and investors' money on the line using this approach to build the system. And it is very much based on the idea that with the lean startup approach, you don't know until your users start using the system what you need. Which is why composable microservices mean you don't waste money. Okay, that's links to various things that I've talked about. So thank you very much.
If I only press the button, really good stuff. Thank you a lot, Richard. Let's see the questions.
I was curious how you handle failures of microservices when you have asynchronous messages and composition. say you're down 3 microservices in the call stack, but you need some sort of error message on the UI, because one of them or more of the microservices failed. And how do you transport that?
Okay, so the specific, there's a bigger issue around error messages, but specific to the user interface, the user needs to see a message coming back for sure. Most of the time, microservices that are building and displaying the user interface are sending synchronous request-response style messages to microservices that are deeper in the system. So one of the things this architecture does is a lot of the blogs and literature that talks about microservices tends to have a very flat model where most of the microservices are serving up like a web page or serving an API endpoint. This model creates a slightly different structure where 80% of the microservices are internal to the system, which means that there's a whole bunch of asynchronous stuff happening internally, but 90% of the time at the user interface layer, it's that request-response asynchronous style message. So you will get a response back. If you don't, then it times out. That's another type of error. Sometimes you might trigger the error yourself. If you're under too much load, then you throttle the messages and you just drop some of the other messages on the floor. There is one other aspect to the error handling which you need to accept in this system. Because there's a network involved, there's always going to be a certain failure rate. It doesn't matter how good you build your system. You're going to lose a certain percentage of messages, or a certain percentage of messages are going to double up. And this makes people very fearful. This makes people scared because in a traditional software project, you feel like you can design a 100% correct system. Well, maybe you know it's impossible, but you still try to. You still have lots of unit tests. You still have a good specification. But that is a business mistake. So if you think about any business on this planet, pretty much any business, there is always an error rate in everything. In fact, there is a law in the United States covering supermarkets that says they are only allowed to have 2% of their prices incorrect, on barcodes. But think about what that means. That means that up to 2% of prices are incorrect, or can be. It means that they're already accepted. So if you build a software system that is trying to get 100% of the prices correct, it's wasted effort. A lot of the times when I go into clients and they start talking about, the system has to be perfect, you start asking them about their business and you start asking them about error cases and what happens. And then it turns out there will always be errors.
Yes, I agree on the failure rate, but I was curious on the handling logic, like if you do retries, if you set timeouts, if you pass error as messages, and they're also handled by microservices, and then how do you match the event that triggered the error with the error that's on the message bus? You need some sort of state, some sort of session.
Yes.
Maybe somebody has 2 tabs open in the UI.
Good, really very good questions. So this is where we get to practical implementation questions. On the tracing and figuring out what's going on in the system, you need to trace the message flows. So, for example, Twitter open sourced a thing called Zipkin about a year ago, maybe 2 years ago, which embeds little bits of metadata in all the messages. So you can trace their entire flow through the system. And then, what happens is each microservice emits a small UDP message to say, I saw this message at this time. But you sample them, you don't do it for 100%. You only do it for, depending on your flows, you might do it for 1% of messages or 5%. So you can start to understand what your system is doing. And of course, if there's an error, then you definitely want to send that up to log entries or whatever. The other lesson that I've learned is retries are really dangerous. So it's a natural to think I'm on the network, and sometimes messages didn't get through, so I'll try again. But you usually end up in a situation where you overload your own system, because there's usually an issue on the other side, which is probably a bug. That's the reason it can't process the message. So if you just keep sending more and more messages, this microservice triggers the bug in some way and it's sending messages, and the other one, which is scaling, starts sending messages as well, and then this one, and then your whole system falls over. So rather than retry, I would just fail.
Yeah, you fell fast, but this is all complex logic, so I was hoping maybe the infrastructure would handle it, so we wouldn't build it in microservices. Maybe have some sort of exponential backoff or whatever.
Yes, exactly.
But all the glue, it seems to be more complex than it looks like. So is there any open source implementation that we can start with, the Seneca.js or?
Yeah, so I mean that's you can use that straight away. But I mean, I think a more interesting mechanism. So that was built. That's 7 years old. That framework. And we keep it updated, obviously. But I think today, if you were going to start building with the microservice idea, serverless architectures are probably the best place to start. Because a lot of the infrastructure that open source project gives you now comes for free, right? Amazon gives it to you and Google gives it to you. Not everything, and they don't do the pattern matching piece, which you would still have to do yourself and figure out how to do that. But it's a lot easier than it used to be. It's a lot easier now.
Okay, thanks.
Okay.
I have a major problem with the definition of the microservice as a function from a message to a message, and I would say this is wrong except for trivial cases. The correct signature would be it's a function from microservice state and message to a new microservice state and a message. Because the microservice keeps the state in most situations, right? Do we agree here?
Yes, so that there are microservices that change state. But you tend to isolate them into certain parts of the system. It's funny, so approaching this, when you start building things in this way, it does force you to have to build things in a particular manner. So if a microservice is stateless, it really fits this model really well. So you kind of get forced into writing more stateless things. So if I have a piece of business logic, the first thing I will think about is, can I write this as a piece of business logic where everything I need comes into me through a message? Then I write my rule. So one of the other examples I use is sales tax calculations. So I have particular rules for different countries that can be quite complex. It's easy in Europe, really hard in the US because every state has its own rules. I express those rules as microservices embedded in code rather than putting them into state. Rather than saying the interest rate is in a database that I look up, the interest rate is actually inside the microservice. And when it changes, I deploy a new microservice instead. So that makes me stateless. But you're correct. Up the base layer, there are microservices that do change state. It's a strong metaphor, I think, but it isn't pure mathematics for sure. But again, you see, the very fact that that we can talk about that is based on the fact that we've created a model. The model has edge cases and weaknesses, but it gives us an ability to talk about the model no matter what the programming language is, no matter what the system is. As opposed to, do we use annotations in this Java object to implement something, which is too detailed.
Okay, so we agree that at least some services have state, and then I would argue that the idea of running microservices with the synchronous API, stateful microservices with synchronous API, this is again fundamentally wrong, because then you put a lot of coupling in your system and a lot of.
Oh, we're using the word. We're using the word state in the wrong way. I never maintain in-memory state. So the microservice itself.
It doesn't
its state is always persistent.
It's a state and it's synchronous access to that state. And I've seen you drawing a system with synchronous access to microservices. So in the system there was synchronous messages towards some services. And How can you draw a distributed system with synchronous messaging between the components? Because this is what you have. I mean, it's.
What's the negative? What's the negative result?
You need some synchronization once you have synchronous access to a certain message, to a certain microservice.
But the synchronization isn't bad by itself. It's appropriate to some use cases like the user interface.
Synchronization in a distributed system is a major problem.
But there's a difference between being a theoretical problem and a practical problem. So the user expects a synchronous response. If you're having an issue there, sometimes the wrong data comes back. So Twitter is a good example, right? Despite the fact that often in the early days of Twitter, when they hadn't scaled out their system properly, you'd sometimes see wrong tweets, or you'd follow somebody and the follow wouldn't go through, or you'd see the fail whale. It didn't matter. Sometimes the business problem is not the same as the technical problem.
Okay, but where I want to go to is that, from my perspective, microservices always have to have an asynchronous API, always.
Why?
And always have to, because they manage state in somewhere. Some of them are stateless, but some of them have state, and synchronous access to state is the thing that destroys our systems and makes our problem. Anyway, we probably can
But how does it destroy the system?
Yeah,
If it leads to data corruption, then you say, oh, it's 1% data corruption is acceptable. You've nearly won the book. You've nearly won the book.
Let's leave the chance to others to get the book, to win the book, who has more questions. Okay?
Hello. I have two questions actually. The first one would be, how do you achieve this transport independence?
Yes,
Because everything
fantastic question.
in real life.
In real life, okay. In real life, so for a long time, we used DNS, and ultimately, each microservice had a little bit of internal logic in the abstraction layer, hard-coded list of the services. Or, we used message buses, so it would know the topics in RabbitMQ, that sort of thing. But hard-coded.
That means you have to know which
Exactly.
MQ system will be used.
You have to know. You have to know all that stuff. Yes.
Yeah.
So I wasn't happy with that. And about 3 years ago, I was at a talk at a conference by some of the Uber people, and they were talking about a gossip protocol, a service discovery gossip protocol that they were using, called SWIM, S-W-I-M. I can't remember exactly what it stands for, but it's the system that we use now. So the message abstraction layer, which is a utility library in each microservice, joins a gossip network. And each microservice says, these are the patterns that I can handle. And that information through the gossip protocol extends through the whole network. So every microservice in the abstraction layer knows this particular pattern needs to go to this place. Now, you can have, if you have 10 instances of the same pattern, that's just held as a routing table. It's comparable to, I don't know if anybody's used Hystrix, which is a Netflix intelligent load balancer. So it's kind of comparable to that, where instead of having a separate load balancer, the load balancer is a library inside the microservice process. So there's two levels. There's one level where there's total knowledge. And you know the IP address of the service, and you know it's RabbitMQ, or you know it's HTTP. But then there's another level, which is the business logic level, which is abstract. So when I write my code, I don't include HTTP calls anywhere. I don't connect to RabbitMQ. I don't do anything. I just write code that has one function that says send a message. And the library knows how to send it. So I can write unit tests where there is no infrastructure. The sending and receiving piece is completely mocked. It does nothing, there's nothing behind it, it's fake. But I can verify my business logic 100%. When I deploy the system or run it on staging, I add in the library that does all the sending. That gives me enough of the independence and the pattern matching. It's something I've been using for about 2 years now. It works very, very well. But you don't need to go that extreme, right? The service discovery features on Kubernetes or using console or etc. things like that, they also work really well so long as you put them into the abstraction layer, as long as they're not in your code.
Okay, and the second question would be, how do you achieve transaction consistency over multiple microservices if something fails? So we have microservice A, which writes to a database, microservice B writes to another database, and you should have another microservice C that ensures eventual consistency, but this one has to know of both databases.
So you can't, that's the answer, you can't. So if you want a proper transaction, you have to put it all into one microservice. But then the next question you ask is, okay, we have all these other benefits. How badly do we need transactions? So there's usually a small part of your system needs transactions. But there's other parts of your system where you can use different algorithms. So you can do reservations. So you just mark that you're interested in changing this object. And
accounting and inventory.
Sorry?
Accounting and inventory would be two separate microservices which need badly consistency.
Yes, they do. But here's the thing, right? I wouldn't use microservices to build that system. I wouldn't use microservices to build an airplane control system either. This particular model, and there are different tactics and different strategies that you can use for software development. This particular model solves the problem of rapid development under lots of changing requirements. Even if you're building an accounting system, the requirements piece changes rapidly. I can probably speak about this now because I don't work there anymore. I worked for a company that dealt with legal cases. So if somebody steals something in a shop, it has to go through the data has to go through this system that records their identity and the crime and all this type of stuff. Lots and lots of business logic. And if the wrong person sees the information, then the case is broken, all this type of crazy stuff. For the first 9 months of the project, we ignored that problem completely. Just used microservices, made sure that we got the business logic and the functionality correct. And it was only after we got to that point that we refactored the system, combined microservices to create transactions. Accepted some of the issues, deployment issues, dealing with that. So we went from a lovely microservice system with rapid deployment to a macro service system with a smaller number of bigger services. Luckily, in that case, a lot of that system was on-premise, so it didn't matter as much because the need for rapid deployment wasn't there. So there's never a 100% simple answer. But the problem that this approach solves is that first 3 months, 6 months, 9 months of the project, where you just don't know what you're building. You don't know exactly what you're building. Afterwards, you can do different things.
Okay, thank you.
Okay, anything else? This guy really wants the books. I think you had some competition there, that's why you're like, okay, punch them back. Okay, oh, okay. Did you just raise your hand by accident, or you wanted to ask something? Okay.
So regarding the microservice buzzword, it's quite new, but there is a lot of history in working with distributed systems in a fault-tolerant way in the Erlang community. So Erlang people are doing this for 30, 40 years, I don't know. way too long time, and they have solutions for fault recovery from faulty situations and having systems with big uptime. So I would personally recommend for anybody who cares about modeling their system as a microservice thing to study Erlang, Elixir, and that stuff.
100%. So the setting.js open source thing that I'm showing you is a bad re-implementation of some Erlang ideas in JavaScript. And the whole Erlang OTP thing is an inspiration for what we did here. It's not as good. Erlang is wonderful. It's just, it's hard to get a job. Can I get a beer? Can I get a beer? No? Okay, one last piece of work.
On your previous project, on what servicing, or on what service did you deploy the microservices? Or like Amazon?
Oh, okay. So we use a lot of different configuration management tools over the years. We even wrote our own one. I'm all in on Kubernetes now. I don't agree with some parts of it, but it pretty much solves most of the issues. Google Cloud has a production version. I think Azure and Amazon are still beta. We are moving to the serverless architectures as well. I'm concerned about lock-in on them, but we're evaluating them as well as part of how we deploy the systems.
Time for one last question, maybe. No, Richard deserves a beer. And you guys deserve as well. Really good question so far. Okay, so this isn't by accident, right?
Hey, yeah, so I was wondering, I mean, you gave us a lot of arguments that I understand, like mathematical arguments, why is it good to use microservices, but I need to convince people that don't speak my language about it, and there's a lot of tools missing, of deploying, of managing microservice, of managing the queues, you know, of counting the messages in the queues, of tracking, of these sorts of things. Yeah, so my question is, like, if you have some business arguments on...
Yes. It's a good question. So if a business person has read half the story and is saying to you, you want me to use this architecture, but it's more expensive because I need to use more tools, I need to sign up to Kubernetes or whatever, you should ask the question back, but are we not a professional software development organization? Do we not build software professionally? Should we not have a deployment management system? Should we not have proper monitoring? There's a lot of monolithic systems where you don't have to do this and you end up in a lot of trouble. There's a famous case from a couple of years ago. I think it was 2012 was the year. If you look up Knight Capital, so Knight Capital in Google, they lost $450 million in 12 minutes. They were running 8 high-frequency trading Java servers, and they did an update before the exchange opened, and they correctly deployed 7, and they deployed manually by FTP an incorrect version on the 8th server. And when the trade started going wrong, they tried to roll back, so they deployed the wrong version to all 8 servers. And $450 million later, they were just pulling out plugs. Why? Because they weren't using configuration management. Because they hadn't spent 2 extra weeks investing in proper software control systems. So if you look at that article on Google, it's a good motivation for the business people.
Okay, thank you. If I may just add on that, I'd say that usually if you can put numbers on any technical decision, you can convince any business person. Okay, so I think we're pretty much done. Let's give Richard a big hand for the amazing presentation. Thank you, Richard.
Thank you. Thanks, guys. Fantastic question. Fantastic. Thank you.
Before we do the kind of the closing note, who's gonna take a book?
This man over here, absolutely. It is well earned. Thank you.
Okay, I think in order to close in a proper manner, we should have Danny and
Peter and yeah.
Peter.
And just before the picture, thanks all for coming. We'll prepare a new conference next year too, same format. So we'll wait you next year. I hope you enjoy it. We'll send some feedback email. I'm curious about your opinion about this format of conference. And yeah, thank you for coming. And now, yeah, let's give them a round of applause to our speakers. Okay, so let's have a picture, and then we'll go to a wine or something.